Hello everyone, my name is Swati Khare and I will be discussing the topic of optical fibers.
Today we'll dive into the fascinating world of optical fiber communication systems, which is a cornerstone of modern technology that powers our internet, connects cities, and even helps diagnose medical conditions. Optical fibers are marvels of engineering that use light to transmit data efficiently and reliably. They offer unmatched bandwidth, minimal signal loss, and are immune to electromagnetic interference. In this presentation, we'll explore how light propagates through these fibers and the science behind their design, along with their diverse applications, especially in medicine. Now we'll discuss light propagation through fibers. The core principle behind optical fibers is total internal reflection, also called TIR. To understand this, we'll imagine shining a flashlight into a glass tube at just the right angle. Light inside the tube would bounce off its walls and travel through the tube without escaping. Optical fibers use this same principle. Each fiber has a core, which is the inner layer of the fiber, and a cladding, which is the outer layer. The core guides the light, and the cladding ensures it doesn't escape. This structure forms the basis of efficient data transmission. The light inside the fiber carries digital information, making optical fibers perfect for high speed communication. Now we'll discuss the key parameters of optical fibers. The first one is an acceptance angle. This is the maximum angle at which light can enter the fiber and still be guided effectively. A fiber with a larger acceptance angle has a larger acceptance cone and thus can collect light more efficiently. This is crucial for the performance of an optical fiber. Hence, optical fibers with a larger acceptance angle are preferred. The second property is numerical aperture, also called NA. It is a measure of light accepting ability of an optical fiber. The numerical aperture basically quantifies the fiber's light gathering ability. It is given by the formula Na equal to whole square root of n1 square minus n2 square, where n1 is the refractive index of the core and n2 is the refractive index of the cladding. A higher numerical aperture means the fiber can accept light at wider angles. This improves the flexibility in its usage. The third parameter is mode parameter, also called normalized frequency. This determines how many modes or light paths a fiber can support. It is given by the formula V equal to 2 pi a divided by lambda, where lambda is the wavelength of the incident light used, and a is the core radius of the optical fiber. A single mode fiber has a V parameter under 2.405, so it allows just one path for light, while multimode fibers support many paths for light and have a V greater than 2.405. Now we'll discuss the types of fibers. The first classification is based on the number of modes that a fiber has. The first type is single mode fibers. They have a small core and support only one light path. But because of this, they are ideal for long distance communication and have minimal dispersion. The second type is multimode fibers. They have a larger core and support multiple light paths. Because of this, they are suitable for short distances but are prone to intermodal dispersion. The second classification of fibers is based on the index of the optical fiber. The first type is step index fiber. Here, core has a uniform refractive index. Because of this, light bounces in straight lines. The second type is a graded index fiber. Here, core refractive index decreases gradually from the center. Because of this, light paths curve and thus reduce dispersion. Now, we'll dive into the topic of types of fibers in a little more detailed manner. Fibers can be classified based on several characters, such as number of modes, the material used, and the index of refraction. Understanding these three categories is very important for choosing the right fiber for different applications, ranging from telecommunications to medical imaging. Now we will explore these categories in detail, and I will be explaining how each type is structured, its characteristics, and where they are commonly used. The first classification is the types of optical fibers based on number of modes. Optical fibers can be classified into two main types based on the number of modes they support: single mode fibers and multi-mode fibers. The single mode fibers, also called SMF, as the name suggests, allow only one mode of light to pass through. This is called the fundamental mode. This means that only a single light beam travels through the core at any given time. Now I will tell you all about one application. Due to the limited modes, SMF is ideal for long distance communication. This has especially high bandwidth applications such as internet backbone connections, cable TV, and telecommunications. Some of its advantages are its lower attenuation. Since there's only one mode of light, there is very less chance for dispersion. This results in very low signal loss. High bandwidth. This means it can transmit data over very long distances with higher data rates and reduce dispersion. Since there's only one mode, dispersion, particularly modal dispersion, is minimized, leading to clearer and faster transmission. The second type is multimode fiber, also called MMF. Multimode fibers have a larger core diameter, typically ranging from 50 to 100 micrometers, whereas the single mode fiber have a very small core, typically with a diameter of around 80 to 10 micrometers. The mode of transmission in an MMF supports multiple light modes or light rays that travel through the core. These rays follow different paths which can cause varying travel times. Some of its applications are a- the local area networks, also called LANs, data centers, and within buildings where high data rates are needed over shorter distances. So, MMF is typically used for short distance communications. Some of its advantages are its ease of use. Multi-mode fibers are easier to handle and install compared to single-mode fibers. They are also lower cost. MMF is generally cheaper to manufacture and install because the components like the light source, LEDs, are less expensive. Another example of an MMF over SMF is that less precision is required. The larger core diameter of a multimode fiber allows for easier light coupling from the source. The fundamental difference between single mode fiber and multimode fiber is that the single mode fiber supports only one light path. This makes them ideal for long distance transmission with low signal loss, whereas multimode fibers support several modes, which makes them suitable for short distance communications. The second classification is based on the material used. Optical fibers can be classified based on the materials they are made from. The most common materials used for optical fibers are glass and plastic. The glass optical fibers are made from silica, also called SiO2, or other glass materials that have been specially designed to transmit light effectively. They have lower attenuation rates and can carry light signals over longer distances, making them ideal for high performance applications. They are more durable and resistant to environmental conditions compared to plastic fibers. Glass fibers offer superior bandwidth capabilities, meaning that they can carry more data at higher speeds. They experience much lower signal loss compared to plastic fibers, especially over long distances. Hence, glass optical fibers are commonly used in telecommunications, broadband, internet, and medical instruments such as endoscopes. The second type of fiber is a POF called a plastic optical fiber. Here is a figure of a standard POF cable showing its outer sheath, strain relief using aramide yarn, a POF fiber, and a single core sheath. Plastic fibers are made from polymer materials, typically PMMA, which stands for polymethyl methacrylate. Plastic fibers are much more flexible than glass fibers. This makes them easier to install and handle, particularly in environments where tight bends are required. Plastic fibers are also cost effective as they are cheaper to manufacture and install. This makes them suitable for short range and low cost applications. Plastic fibers are also preferred because of safety. They are less prone to breaking under stress, unlike glass fibers, which can be fragile and broken easily. But plastic fibers also have some disadvantages. That is, they have higher attenuation, which means that they experience a higher signal loss over long distances and have a lower bandwidth. With a lower bandwidth, they cannot transmit data at high speeds, whereas glass fibers can transmit data at very high speeds. Optical fibers are also categorized based on their index of refraction. This refers to how much light is bent or refracted when passing through the fiber. The first type is a step index fiber. They have a refractive index, and the refractive index drops sharply at the core cladding interface. In these fibers, the light travels straight until it reaches the boundary between the core and the cladding, where it undergoes total internal reflection. Step index fibers are often used in telecommunications and local area networks for transmitting light over moderate distances. They are preferred for the simpler design and manufacturing process. Step index fibers are also cost effective for moderate performance requirements. But they have a disadvantage, which is their higher dispersion rate compared to graded index fibers. The second type of optical fiber, based on the refractive index, is a graded index optical fiber. They have a core where the refractive index gradually decreases from the center to the outer edge of the core, creating a gradual index profile. The light inside such fibers follows a curved path as it moves through the core due to the varying refractive index, resulting in reduced modal dispersion and higher data transmission speeds. These fibers are ideal for high speed data transmission, and they are used in applications like high bandwidth internet connections and optical communication systems. They offer reduced dispersion because the gradual change in refractive index in them minimizes modal dispersion. This allows for better performance over medium to long distances and higher performance compared to step index fibers. Graded index fibers support higher data rates and more efficient at transmitting light over longer distances. To conclude the topic of types of fibers, I would like to say that each type of fiber has its own strengths and limitations. And while selecting the right fiber, we have to keep them in mind. The selection of optical fiber depends on the specific application requirements, such as the distance, the bandwidth, the installation cost, and the environmental conditions. Now, I'm going to discuss a critical concept in optical fiber communication systems, that is, attenuation loss. Attenuation loss is a term that defines the gradual loss of signal strength as it travels through the optical fiber. This loss is a natural phenomenon This affects how far and how effectively we can transmit light signals without requiring amplification or regeneration. To understand attenuation fully, we need to examine what causes it and its different types, which I am going to do now. First, what is attenuation loss? This refers to the reduction in the intensity of the light signal as it propagates through the optical fiber. This is usually measured in decimals per kilometer. And second, why does attenuation loss occur? This happens due to three main factors that are absorption loss, scattering loss, and bending loss. Now we will explore each type in detail. Here is a flowchart that briefly describes the types of attenuation losses. The first type is absorption loss, the second type is scattering loss, and the third type is bending loss. There are two types of material absorption losses that are intrinsic absorption and extrinsic absorption. To understand this, first we understand attenuation loss in optical fibers. Attenuation refers to the reduction in the intensity of light signals as it propagates through the optical fibers. This loss is usually measured in decibels per kilometer. In simple terms, attenuation occurs due to three main factors: absorption loss, scattering loss, and bending loss. Let's explore each type in detail. Absorption loss occurs because of impurities in the optical fiber material. These impurities absorb light energy and convert it into heat, leading to a reduction in the signal strength. The first type of absorption loss is intrinsic absorption. This happens due to the natural properties of the glass material used in the fiber. Certain wavelengths of light are absorbed because of the molecular vibrations of the glass. The second type is extrinsic absorption. This is caused by the external impurities, such as metal ions like iron, copper, or water molecules trapped during the manufacturing process. Although modern manufacturing techniques have significantly reduced impurities, absorption remains an unavoidable part of attenuation. The second type is scattering loss. This is one of the most significant contributors to attenuation in optical fibers. It occurs due to microscopic irregularities in the glass structure of the fiber. Rayleigh scattering is the most common type of scattering loss in optical fibers. It occurs when light interacts with variations in the density or composition of the fiber material. These microscopic variations scatter the light in all directions, causing signal loss. Rayleigh scattering is especially pronounced for shorter wavelengths of light, which is why modern fibers are designed to operate at longer wavelengths, such as 1550 nanometers, where scattering is minimized. The third type of attenuation loss is bending loss. Bending loss happens when the fiber is bent too sharply, causing some of the light to escape from the core into the cladding or outside the cladding. The two types of bending loss are macro bending and micro bending. Macro bending is a large scale bend, like when the fiber is coiled or curved too tightly. This causes light to leak out of the core, whereas microbending is tiny and almost invisible. This is caused by imperfections in the fiber or external mechanical forces. Microbending is usually caused during the manufacture of optical fiber. This can disrupt the light path and lead to scattering of the signal. Bending losses are particularly concerning because they can occur during installation or handling of the fiber. So, engineers must follow strict guidelines for minimum bend radii to prevent such losses. We can quantify attenuation using the formula A equal to 10 times log to the base 10 of P in divided by P out, where P in is the input optical fiber and P out is the output optical fiber, and the unit of this is decibels per kilometer. Lower decibel per kilometer values indicate better performance and lower signal loss, whereas higher the attenuation value, the lower the performance and the higher the signal loss. The modern single mode fibers typically have attenuation values of zero point 0.2 decibels per kilometer at 1550 nanometers. The effects of attenuation include reduced signal quality over long distances, the need for repeaters or amplifiers to regenerate the signal, which adds to system complexity and cost, and the lower efficiency of communication systems, especially at high speed. In summary, attenuation is an inevitable challenge in optical fiber communication, but understanding its causes, such as absorption, scattering, and bending, helps us design better systems to minimize its impact. By using high purity materials, optimized wavelengths, and proper installation techniques, engineers can reduce attenuation and ensure efficient, high speed data transmission. I hope this explanation clarifies the concept of attenuation loss and its types. The next topic is dispersion. Dispersion refers to the spreading of light pulses as they travel, which can blur the signal. There are two main types of dispersion: intermodal dispersion and intramodal dispersion. Intermodal dispersion occurs in multimode fibers because different light modes travel different distances. This results in signal overlap and is more prominent in step index fibers, whereas intramodal dispersion affects single mode fibers. This arises from material properties such as different wavelengths that travel at different speeds and waveguide effects. By understanding and minimizing these losses, that is, dispersion and attenuation, engineers have made optical fibers the backbone of global communication networks. Now we'll discuss the last topic, that is, applications of optical fibers in medicine. The most exciting application of optical fibers is endoscopy. Optical fibers are widely used in endoscopy, a diagnostic tool that allows doctors to visualize internal organs without invasive surgery. A bundle of optical fibers transmits light into the body, while another bundle collects and relays the image back to the doctor. This innovation has revolutionized medical diagnostics, enabling safer and more accurate procedures. To summarize, flexible fiber bundles are used for diagnostics because they are minimally invasive, safe, and very effective. The other applications of optical fibers are laser surgeries, dental procedures, and phototherapy. To summarize the topic of optical fibers, optical fiber communication systems are engineering marvels that harness light for efficient, high speed data transfer, from the principles of light propagation to the design parameters like numerical aperture and mode parameter. These fibers are carefully engineered to minimize losses like attenuation and dispersion. Beyond communication, their application in medicine, particularly in tools like endoscopes, highlights the transformative impact. Thank you for your attention. I hope this discussion has illuminated this incredible science and versatility of optical fibers.